Alright, another example of calculating volumes using cylindrical shells. Here's the region, here's the axis of rotation. Let me draw the figure and I'll speed this up while I draw it. Okay, so that's the volume that we have to calculate. And what's different about this example is my axis of rotation is parallel to the x-axis, but the procedure is the same. So to construct the cylinder, we draw a line through the region that we rotated parallel to the axis of rotation. So here's my line, and so this point is going to go down here, and that is the cylinder. The radius of the cylinder is this is r, this is the height h, and we now start drawing our rectangles for the coordinate systems. So this point has those coordinates in the rotational coordinate system. I'm going to call that length h2 from here to here. This is r. So this has coordinates h2 comma r. In the original coordinate system, that's the rectangle, and I'll say this has coordinates x2, y2. So this is x2, this is y2, and we can write down the basic relations. So h2 is the same as x2, y2 plus this distance, which is 1. It's the distance of the axis of rotation from the x-axis. y2 plus 1 equals r. So r equals y2 plus 1. And because this point is on this line, x2 equals y2. So that's our first relation. To get the second relation, we look at the other end of the cylinder, and that end is here. Its coordinates in the rotational coordinate system are given by this rectangle, and let's see if the height from here to here is h1. This is of course the same as r. It's the same radius of the same cylinder. So the coordinates of this point in the rotational coordinate system are h1 comma r. Let's say that in the original coordinate system the coordinates were x1, y1, then that would be this rectangle. So this is x1, this is y1, and now you can see the relations here. So x1 is the same as h1, r is the same as y1 plus 1, and because this point lies on this curve, y1 equals square root of x1, and the h, the thing that we're really interested in, is just h2 minus h1. So of course we find h2 as a function of r and h1 as a function of r as the next step. So h2 is x2, which is y2, which is r minus 1. h1 is x1, and x1 is y1 squared. y1 is r minus 1, so this is r minus 1 squared. So this, as before, is r minus 1 minus r minus 1 squared. And we also need the limits of r. So r, according to this, is y2 plus 1. And y2 is this distance. It's the y coordinate of the points on this line. So the smallest y2 is here at the origin of the original coordinate system, and that's 0. The largest y2 is up here, which is the intersection of this, and that point is just 1, 1. So again, the smallest value of r is when y2 is 0, so it's 1. The largest value of r is when y2 is 1, so it's 2. So our limits of integration are 1 to 2. And so now the volume is 1 to 2, 2 pi r h dr, which is 2 pi integral 1 to 2 r minus 1 r minus 2 square dr. And that integral is exactly the same integral as in example 1, and you can look at that example and see how we do that.